What if the first confirmed interstellar object we ever studied didn't behave like a rock at all, but like something that was deliberately adjusting its path toward us? At the Minor Planet Center in Cambridge, Massachusetts, the morning begins like any other. Screens glow with endless streams of orbital data, and scientists quietly track the predictable motion of comets, asteroids, and distant fragments that drift through the solar system. At TIA 48 AM UTC on the 13th of April 2026, a senior orbital dynamicist named David is going through routine updates, comparing orbital eccentricity values with known Kuiper belt objects. It is repetitive work, the kind of task that normally confirms how orderly the solar system really is. He takes a slow sip of water, eyes scanning numbers that usually describe nothing more than gravity doing its job. But then something changes. A new entry appears on the screen, linked to an interstellar visitor labeled 3 Atlas. In that moment, the atmosphere in the room subtly shifts, although no one else has noticed it yet. David's hand freezes. What he is seeing does not match any known pattern of natural motion. The data does not show a normal hyperbolic escape trajectory, the kind expected from an object just passing through the solar system. Instead, it shows something that should not exist in classical orbital mechanics. A controlled deceleration happening in deep space with no visible cause. The velocity has dropped by exactly 12.4 kilometers per second. No fragmentation, no outgassing, no sign of natural braking forces. Just a clean, precise reduction in speed, as if something has applied a calculated correction. Then comes the second alert. A classified circular from the International Asteroid Warning Network appears in the system. David has been in this field for 20 years, and he has never once seen this level of classification attached to an interstellar object. And then the third detail arrives, the one that changes everything. For the first time in recorded history, an interstellar object has been moved from the passive observation list to the active threat tracking system. This is not routine classification. This category is reserved for objects that carry a non-zero probability of Earth impact. The room suddenly feels smaller. David pushes his chair back with a sharp metallic sound that cuts through the silence. He does not call a meeting. He does not wait for confirmation. He reaches for a secure redline phone, a direct link to NASA's Planetary Defense Coordination Office. His voice is controlled, but tight. "We have a maneuver," he says. 3 Atlas is not leaving, it's intercepting. That sentence lands like a weight no one expected to carry this morning, because it raises a question that no one is ready to answer. What kind of natural object changes velocity in deep space without shedding mass or reacting to a star's gravity? And why is the Global Planetary Defense Network suddenly redirecting its attention toward a single point in the sky? Within hours, the shift becomes official. This is no longer an object of curiosity. It is a monitored threat. The scientific community is no longer simply observing the universe. It is preparing for something approaching it. And at the center of it all is a simple but unsettling realization. Something out there is not just passing through space. It is adjusting its course. Within hours, the situation stops feeling like an isolated anomaly and starts looking like a coordinated global response. What was once a quiet stream of astronomical data becomes a synchronized alert system across institutions that normally do not react with urgency unless something truly extraordinary is happening. At the Minor Planet Center, the initial confusion turns into structured escalation. Planetary defense protocols begin activating in layers, each one designed for a different category of risk. Normally, these systems are used for near-Earth objects, asteroids formed from the early solar system, bodies that follow predictable paths shaped by the sun's gravity. But 3 Atlas does not fit that category at all. It entered the solar system at an extreme velocity, measured at 60.2 kilometers per second, arriving from the direction of the constellation Sagittarius. That alone already places it in a rare class of interstellar objects. But what is happening now is far more unusual than its origin. The data being analyzed shows that this object is not simply passing through. It is behaving in a way that suggests control over its own trajectory. That single detail forces scientists to move beyond standard models of orbital mechanics. In most cases, when an object enters a star system at interstellar speed, it follows a hyperbolic path. It swings through the system and exits, driven only by gravity. It does not slow down unless something physical forces it to. But here, the deceleration is precise, consistent, and unexplained. There is no visible gas plume, no breakup, no thermal signature consistent with mass loss. In other words, nothing that would normally account for a change in momentum. And yet the change is real, measurable, and ongoing. This is where planetary defense stops being purely observational and becomes interpretive. Scientists begin to consider whether they are dealing with something that is not just following physics, but interacting with it. Some models, including simulations referenced in advanced research frameworks like the Galileo project, begin to treat the event not as a collision risk, but as a signal. A signal implies intent. That idea changes everything. Within this framework, the deceleration is no longer just a physical anomaly. It becomes a potential techno-signature, something that suggests engineering rather than randomness. A rock cannot decide to slow down in deep space without an external force. So the question becomes unavoidable. If this is not a rock behaving naturally, then what is it? The discussion begins to shift into more speculative but structured scientific language. Some researchers reference classification scales popularized by theorists like Michio Kaku, where civilizations are ranked by their ability to manipulate energy and space itself. In that context, an object capable of controlled interstellar deceleration begins to resemble something associated with advanced technological systems rather than natural formation. One hypothesis emerges cautiously within simulation environments: the possibility of a mechanism that interacts with vacuum energy or uses an unknown form of propulsion, something far beyond chemical or nuclear processes as currently understood. Another suggestion is even more extreme, involving manipulation of space-time geometry itself, where the object is not slowing down in the traditional sense, but shifting through layers of physical reality in a controlled manner. At this stage, nothing is confirmed. Everything remains within the boundaries of modeling and interpretation, but the direction of analysis has clearly changed. What began as routine asteroid tracking is now a coordinated attempt to understand whether humanity is observing a natural object or the behavior of something engineered. And as the global telescope network narrows its focus, another detail emerges that deepens the mystery further. The object's trajectory is not random. It is gradually aligning toward a shared orbital plane, one that intersects with Earth's long-term motion around the Sun. That alignment forces a difficult question onto every system now watching it. Is this simply a coincidence of cosmic motion, or is it a path being chosen? For the first time since detection, the scientific community is no longer debating what the object is made of. They are debating what it is doing. As more observatories join the tracking effort, the situation evolves from a single anomaly into a fully coordinated global observation event. Telescopes in Hawaii, Chile, and across Europe begin feeding synchronized data streams into shared defense systems, not to predict curiosity-driven behavior anymore, but to continuously update a potential risk profile that is changing in real time. At this point, 3 Atlas is no longer being treated as a passive interstellar object. It is being treated as an active system with evolving behavior. The reason is simple, but deeply unsettling. The object is not just moving through space, it is interacting with it. Radar and optical reconstructions from the Goldstone facility begin to reveal inconsistencies in its structure. What was initially assumed to be a natural comet-like body no longer behaves like one. The surface does not reflect light in a uniform way. Instead, there are patterns, sharp angular returns that suggest flat surfaces, or at least geometry that does not belong to naturally formed ice or rock. Then comes another development that shifts the tone in every control room watching the data. A weak electromagnetic signal, initially detected near 1,420 MHz, begins to evolve. At first, it appears random, like background noise or interference. But over time, it shows structure, repetition, then coordination. Eventually, it is no longer just a signal, it resembles a pattern of intentional communication. Some researchers cautiously describe it as a handshake-like sequence, not because it confirms communication in any human sense, but because it behaves like a system attempting to establish alignment with another network. That interpretation changes everything about how the object is perceived. If this is not noise, then it is information. And if it is information, then something may be attempting to interact with us. At the same time, orbital simulations begin to show a more precise and concerning trend. The object's path is not just bending toward the inner solar system, it is gradually aligning with Earth's orbital plane. That kind of convergence is statistically rare unless influenced by external control or extremely specific initial conditions. For planetary defense analysts, this is where abstraction becomes urgency. The International Asteroid Warning Network escalates its monitoring protocols again, not because an impact is confirmed, but because the behavior no longer fits any known category of natural motion. And still, no one can explain the energy problem. To slow an object of this estimated mass at interstellar velocity would require an energy output so extreme that it would normally produce detectable thermal destruction. A natural comet would disintegrate under such forces. Yet no such debris, vaporization trail, or thermal shock signature is observed. This leads to one of the most controversial theoretical possibilities being discussed in simulation environments, that the energy is not being released in conventional space at all. Instead, some models suggest it could be dissipating through higher dimensional interactions, effectively transferring energy into states of physics we do not yet understand or cannot directly observe. This remains purely theoretical, but it reflects how far interpretation has already stretched. Meanwhile, the Global Observation Network continues to tighten its focus. Every major telescope is now part of a single distributed monitoring system. The object is being tracked continuously, with recalculations of its trajectory updated hour by hour. And as data accumulates, another pattern begins to emerge, subtle but persistent. The object is not just approaching, it is timing its approach. It appears to be synchronizing its motion with Earth's position in orbit, as if preparing for a specific alignment rather than a random pass-through. At this stage, the scientific language begins to shift again, not toward certainty, but toward recognition that something unprecedented is unfolding. Because whatever 3 Atlas is, it is no longer behaving like something that simply arrived in our solar system. It is behaving like something that knows exactly where it is going. As the tracking systems refine their projections, the tone inside global observatories shifts again, becoming quieter, more focused, and far more cautious. What began as curiosity has now become sustained, high-priority monitoring of an object that refuses to behave like anything in recorded astronomical history. 3 Atlas continues its inward journey, but the deeper the analysis goes, the less it resembles a natural interstellar body. The shape of its behavior is becoming just as important as its physical properties. High-resolution radar from facilities like Goldstone begins to reveal something even more unexpected. The object's surface is not only irregular, but structured. Certain reflections suggest flat planes, right angles, and geometric consistency that does not align with known asteroid composition or comet fragmentation. Instead of erosion or chaotic breakup patterns, there are hints of ordered design. This forces a difficult shift in interpretation. Scientists are no longer just modeling orbital mechanics. They are now evaluating whether the object has an internal structure that maintains itself against external forces. At the same time, the electromagnetic data grows more complex. What started as faint, low-frequency patterns has developed into layered signals that appear structured across multiple bands. Some researchers cautiously describe it as a form of broadband interaction, where the signal does not simply broadcast outward, but seems to respond to incoming observations. This is where the concept of a handshake becomes more than a metaphor. In network theory, a handshake is a process where two systems establish communication parameters. But here, nothing about the system is understood well enough to confirm intent. Still, the behavior resembles synchronization attempts, structured, repeating, and increasingly stable. And then comes a far more unsettling observation. As Earth-based telescopes continue to refine their data, the object's trajectory shows a deliberate convergence toward a gravitationally stable region near the Earth-Moon system. More specifically, calculations suggest alignment toward the L1 Lagrange point, a position where gravitational forces between Earth and the Sun create a kind of equilibrium zone in space. In orbital mechanics, Lagrange points are valuable because they allow objects to remain relatively stable with minimal energy input. For scientists watching this unfold, the implication is difficult to ignore. If the object is intentionally adjusting toward that region, it suggests a level of navigational precision far beyond natural drift. Meanwhile, another layer of analysis begins to challenge even that assumption. Thermal imaging and spectral data suggest that the object is undergoing structural change, not fragmentation, but transformation. As it approaches key points in its trajectory, its reflected signature shifts, as though its surface geometry is reorganizing itself under stress or command. Some models attempt to explain this through advanced material physics, suggesting adaptive structural response to external radiation or gravitational gradients. Others go further, speculating about self-reconfiguring systems, structures that change form based on environmental input rather than resisting it. None of these interpretations are confirmed, but all of them reflect the same underlying issue. The object no longer fits into a single category: comet, asteroid, probe, or something else entirely. Each label begins to fail under the weight of new data. And as the monitoring network expands its computational resources, a disturbing realization begins to emerge among some analysts. The object is not just being observed anymore. It is, in a very technical sense, interacting with the observation process itself. Subtle correlations appear between measurement cycles and signal variations. Timing anomalies begin to align with observation windows. Even radar reflections show minor inconsistencies that correlate with when and where Earth-based instruments are focused. At this stage, one idea begins to circulate carefully through scientific discussions, never stated as fact, only as possibility. What if 3 Atlas is not simply traveling through the solar system? What if it is responding to it? And as this question takes hold, the distinction between passive object and active presence becomes harder to maintain with certainty. By the time the global monitoring systems reach full coordination, 3 Atlas is no longer treated as a single object under observation, but as a continuously updating system that must be tracked across multiple layers of interpretation. Every major observatory now feeds data into shared models that recalculate its position, structure, and signal behavior almost in real time. At first glance, its trajectory still appears consistent with orbital physics. But beneath that surface consistency, something far more complex is unfolding. The object is not simply following a path through space, it is adjusting that path in ways that suggest continuous feedback with its environment. The most striking development comes from the growing complexity of the electromagnetic activity. What was once a faint signal near 1,420 MHz has expanded into a broad, structured pattern that no longer behaves like random emission. Instead, it shows repetition, modulation, and timing that suggest layered encoding. Researchers remain cautious in their language, but internally, many begin comparing the structure to a diagnostic exchange rather than a simple broadcast. It behaves less like noise and more like a system testing responses, refining output based on what it receives back from its surroundings. This interpretation becomes harder to dismiss when combined with orbital behavior. As 3 Atlas approaches deeper into the solar system, its path begins to align with increasingly precise gravitational targets. The convergence toward the Earth-Moon system becomes more refined, as if each adjustment is correcting toward a pre-calculated destination. In planetary defense simulations, this level of precision is extremely unusual. Natural objects do not typically refine their trajectory in response to small-scale gravitational mapping unless acted upon by a consistent external force. Yet no such force is detectable in conventional terms. This leads to another theoretical branch of analysis, where researchers consider whether the object might be using unknown forms of propulsion or space-time interaction. Some models explore the possibility that it is not pushing through space in the traditional sense, but instead altering local space-time geometry to step between stable orbital positions. These ideas remain speculative, but they are being discussed because simpler explanations are failing to account for the data. At the same time, high-resolution scans from Earth-based radar networks begin to reveal more detailed structural anomalies. The surface is no longer interpreted as irregular rock. Instead, it shows consistent angular geometry that appears too ordered to be the result of natural formation alone. Flat regions, repeating edges, and symmetrical features suggest an internal coherence that resists external disruption. As these findings accumulate, another subtle but significant pattern emerges in the observational data. The object appears to respond differently depending on how it is being studied. Certain measurement intervals produce slightly altered signal outputs, while specific observational angles correlate with shifts in electromagnetic activity. This raises a difficult question within the scientific community, one that is carefully avoided in official statements but increasingly discussed in private analysis sessions. Is the object simply being observed, or is it aware of the observation process in a functional, physical sense? No one claims consciousness or intent in a human framework, but the data suggests a system that is at minimum reactive to measurement inputs, capable of adjusting behavior based on external detection. At this stage, classification becomes increasingly problematic. The traditional categories of comet, asteroid, or spacecraft no longer provide a stable framework for interpretation. Instead, analysts begin referring to it in more neutral terms, an active interstellar system with adaptive behavior. And as the object moves closer to its projected orbital convergence zone near Earth's gravitational environment, the stakes of interpretation rise sharply. Because if these patterns continue, then the final question is no longer about what 3 Atlas is made of. It becomes a question of what happens when it arrives at the point it appears to be aiming for. As the projected convergence window draws closer, global observatories enter a state of continuous tracking where no single institution is working in isolation anymore. Instead, data flows in a shared loop between continents, forming a unified planetary observation network focused entirely on 3 Atlas. At this stage, even the language used in internal reports begins to change. Words like object and trajectory start to feel insufficient. The reason is simple. Nothing about the data remains stable enough to be described with traditional assumptions. 3 Atlas is still approaching, but it is not doing so passively. Every updated calculation suggests refinement, as if its path is being corrected repeatedly with knowledge of its environment. These are not random deviations. They are structured adjustments that keep aligning it with a narrow region of space near the Earth-Moon system. Particularly, attention centers again on the L1 Lagrange point. This region, where gravitational forces between Earth and the Sun balance in a stable equilibrium, is not just mathematically interesting, it is operationally significant. Satellites positioned there remain relatively fixed with minimal fuel consumption, making it a strategic location in space infrastructure. The concern among analysts is not simply proximity, it is precision. The object is not passing near this region, it appears to be targeting alignment with it. At the same time, the electromagnetic signature continues to evolve. The earlier narrow band pattern has now become a layered structure of signals that appear increasingly organized. Some researchers describe it as a multiplexed transmission, where multiple streams of information seem to be embedded within a single expanding waveform. In parallel, timing correlations emerge between signal variations and observational events on Earth. When telescopes shift focus, when radar intensity increases, or when tracking algorithms update, subtle changes appear in the signal pattern. These correlations are small, but consistent enough that they cannot be easily dismissed. This leads to one of the most sensitive discussions in the entire analysis effort: the possibility that the object is not only emitting data, but responding to data collection itself. No formal conclusion is reached, but the idea reshapes how every subsequent observation is interpreted. Meanwhile, structural imaging continues to reveal new complexity. High-resolution radar suggests that the object's outer layer is no longer static. Instead, it appears to be undergoing controlled geometric reconfiguration. Certain regions reflect differently depending on viewing angle, suggesting surfaces that may be actively adjusting orientation or composition. Some theoretical models attempt to explain this through advanced adaptive materials, systems capable of restructuring at microscopic levels in response to external forces. Others propose something more extreme, that the object may be maintaining structural integrity through dynamic control rather than fixed composition. At this point, even the most conservative interpretations acknowledge a fundamental limitation. There is no known natural process that can fully account for all observed behaviors simultaneously. Controlled deceleration, structured signal emission, adaptive geometry, and precise orbital alignment. Each piece alone might be explainable. Together, they form a pattern that resists simple classification. And as the object crosses deeper into the inner solar system, another layer of complexity emerges. Gravitational models begin to show that its trajectory is not just intersecting Earth's orbital environment, it is synchronizing with it. The timing of its approach aligns increasingly closely with Earth's position around the Sun, reducing uncertainty in a way that suggests calculated coordination rather than incidental motion. This is where planetary defense logic reaches its limit and transitions into something more uncertain: interpretation under incomplete information. Because at this stage, the question is no longer whether 3 Atlas will pass near Earth. It is whether its arrival at this specific region of space is accidental at all.